Hey everyone, this video is going to introduce Lab 5, which is going to be about friction. The point of this lab will be first to calculate the acceleration of an object which has friction acting on it, and second to measure that acceleration to confirm the calculation. So a classic, use the theory to calculate what you expect the acceleration to be, and then measure that acceleration to confirm that you understand the theory. The situation we're going to study will have a table right here with a pulley, two objects, M1 and M2, of masses which we know, and the masses are going to be connected by a string. So, as M2 falls, it is going to drag M1 with it. M1 is going to have some friction on it because of its contact with the table, and we want to find the acceleration of the whole system. So the first thing to understand, of course, is that the acceleration is going to be the same for M1 and M2 because they are connected by a string. That prevents the length between them from changing, and so the acceleration will be the same. So, just like any of our whiteboard problems, we have a process to solve this problem. First step is to find a free body diagram. Of course, there's a step that might be right before that, which is to define a coordinate system. So the coordinate system is going to be a choice. So we haven't emphasized this too much in class yet, but the coordinate system is a personal choice, your choice. Only you can pick the coordinate system. There is an infinite number of coordinate systems for any given problem. Normally one or two of them is going to be the best choice, but if you make a coordinate system choice, you can do the problem in that coordinate system. It's an important thing to remember that you can pick it, doesn't matter what you pick, you'll be able to do the problem, but in some cases, there are better choices than others. You need a coordinate system for every mass. So in this case, what I'm going to do is I'm going to pick this coordinate system for this mass, which is the sort of x and y standard coordinate system. I'm going to pick a slightly different coordinate system for the second mass, one which has x and y tipped. So you can sort of think of this as starting here and as it goes, tilting, so the x direction stays along the string. And that's really my coordinate system, is actually x direction along the string. Why am I picking this? Well, there's lots of reasons, but for one, you can just see immediately that if I have an acceleration of m1 in the x direction, that's going to correspond to a positive acceleration of m2 in the x direction. And that's just going to make things a little bit easier. Could have done a different choice, would have ended up with different equations, but it still would have been the right answer. Alright, here's the free body diagram for the first mass. Why is this the free body diagram? Well, I started just by drawing the vertical parts because I know them, FG, FN. They're the same length because the thing is not accelerating off the table. And then I wrote tension of the string and the force of friction. Tension of the string is bigger than the force of friction because we expect the thing to move. There's the free body diagram for the second mass. I've written FG as being bigger than the tension. This is just so that the thing actually accelerates because we want the thing to accelerate downwards. So those are my two free body diagrams. Next step in the process, this is not unique to this problem, this is the process for every single problem that we have forces, is of course writing down Newton's second law. Newton's second law being of course that the sum of the forces is mass times the acceleration. You'll get a Newton's second law for every free body diagram. We have two free body diagrams. A Newton's second law has two components, x and y, so that means in principle there could be four Newton's second law in this problem. You should immediately be able to see that one of Newton's second law is not going to give you anything since there's no horizontal component here. There's no horizontal component for M2 in Newton's second law. So in other words, I'm saying that in this situation we have three equations for Newton's second law. The third step in any problem is to solve. So this just means figuring out what you have and what you need. So I'm asking what the acceleration is. So in this case, we are solving for A. But in the lab, we're going to have to do something very specific. We want to solve A in the most general case, right? So that means we want A as a function of the other variables we have in the problem. So this is going to be a function of the frictional force, function of m1, and a function of m2. You should have an equation which has m1 and m2 in it. Now, of course, instead of m1 and m2, you might decide to use the weight of the object. So you might decide that you actually want to use w1 and w2. That's a choice because you can convert between the weight and the mass just by multiplying times the acceleration due to gravity. But you need to write an equation for the acceleration in terms of those three variables. And then we're going to go into the lab and we're going to figure out what that force of friction is. We're going to measure that. And then once you have measured the force of friction, measured the weight of the two objects, then you can calculate what A is. Then you can perform the experiment and check to make sure that the acceleration is what you expect it to be. And I just want to make one note here that I'm being a little bit careless with notation, which I shouldn't be. This should really be labeled FG1, and this really should be labeled FG2. Of course, that's because this is M1 times G, and this is M2 times G. And I should be careful in general, but here specifically, because I have the two tensions here, which are the same due to Newton's third law, those are the exact same magnitudes. I want to make sure that these two F's, we don't think the same thing about them. They should be different magnitudes. One is M1G, one is M2G. So let me introduce you to the lab setup. We have the controller connected to the motion sensor, which is connected to the force sensor as well. We're going to use both in this lab. We have a ramp here, which we're going to slide things down. A friction block with some felt on it, that's going to provide our friction. And then the string is going to go over the ramp, over this pulley, down to a weight, which is going to pull and give us the tension. The first thing we got to do is, switching over to Logger Pro now, we're going to have to make sure this thing is very well calibrated. So that means two things. First, we've got to zero it out. So go to 0. Just run it, it will click for a while, then it'll hit 0. Okay, but we also have to calibrate it. So this means we have to calibrate it with a known mass. I have a 200 gram mass here. 200 grams in newtons is 1.96 newtons. So I'm going to go to 1 point calibration just to save time. You could probably do a 2 point if you wanted. And I'm going to do calibrate now. Make sure that it's as stable as possible. Enter 1.96. Keep. Okay. And our force reading is 1.96. Perfect. So, in order to get the force of friction, you know that if I pull this, it's going to have a pulling force, and it's also going to have a frictional force. Well, if those two forces are equal, you know, I can measure the pulling force just by attaching this thing to it. If I can measure the pulling force using the force sensor, if I can pull the block at a constant velocity, then I'll be able to tell what the frictional force is, because it will be exactly the force that I'm pulling it with. So that's the setup that you want. You want to try to pull this thing with a constant force. So let me try to do that and show you about what it looks like. So start the run. Try to pull it as best you can with a constant velocity. So if you pull it with the constant velocity, the force should be constant. So I'm going to select the force. I'm going to rescale using this A right here. And you can see that my force is not that constant. It's not bad, but it's not great. One thing you can do is you can select an entire region, go up to analyze and do statistics, and then get the average. So yours should be a little bit better than this, but you know, you can see that it's bouncing around, but it's at a relatively constant value, 0.2075. See the mean is right there. So that should be, as long as I could do maybe a better job being this constant, that should be our frictional force. So that's going to be the frictional force that we plug into our equation. So after you solve the equation from the first part, you can get the frictional force, and that will tell you what the acceleration of this system is going to be. After you have that, then you can do the second part of the lab, which is hanging a mass off the pulley down here, putting the motion sensor at the other side, and measuring the position as a function of time of this block, then fitting it with the Logger Pro software, as we've done in the past, and then figuring out what the acceleration is. And then you can check to see if your acceleration that you get from the fit is similar to the acceleration that you're going to calculate from the first part of the lab. I'm not going to go through that because we've done the fitting thing when we did the projectile lab, but that's the basic process. You want to calculate the acceleration based on what the frictional force is that you measure in the first part, and then measure the acceleration by fitting with the Logger Pro software. Okay, great. So that's the overview of the lab, and we will do it on Monday. See you guys.